All right, today we are diving into a totally invisible world, the world of electric potential energy. This is a kind of hidden power that isn't about motion, but about the very position of things. Let's jump in. We've all seen a lightning strike, right? It is just raw, incredible power. It can release a massive amount of energy in a split second. And all of that energy comes from charges being separated between the clouds and the ground. It's stored up in their positions. But before you see that flash, before you hear the thunder, where is all that energy actually? It's just hanging out there, held in the tension in the air. So, how does that work? Well, the answer is electric potential energy. It's this type of stored energy that a charge has just because of where it is in relation to other charges. Now, to really get a good handle on this, let's start with an idea that's a little more down to earth. To understand this invisible energy, we're going to use an analogy that, all of us deal with every single day: gravity. Think about it. When you lift a rock off the ground, you have to do work, right? You're fighting against gravity. But that effort, that energy you put in, it doesn't just disappear. It gets converted and stored inside the rock as gravitational potential energy. The higher you lift it, the more energy it's got stored up. And here you can see the parallel perfectly. On the left, you've got a ball on a hill. It has gravitational potential energy. Simple enough. On the right, you have a positive charge between two charged plates. And believe it or not, it's in the exact same kind of situation. It's basically sitting at the top of an electric hill. The physics behind both of these is pretty much the same. In both gravity and electricity, you're dealing with what's called a conservative force, which is just a fancy way of saying the work you do against it gets stored. It doesn't get lost as heat or something. So when you do that work, potential energy, we'll call it U, gets stored up. And what happens when you let go? Well, that stored potential energy instantly starts converting into kinetic energy, the energy of motion, which we call K. So the loss in potential energy is equal to the gain in kinetic energy. Okay, so you've got that gravity analogy in your head? Good. Now let's leave the regular hills behind and start climbing those electric ones. So an electric field, it acts like an invisible landscape of hills and valleys for other electric charges. If you take a positive charge and try to move it closer to another positive charge, it's just like pushing a boulder up a hill. You're fighting against that natural push-away force the whole time. And just like lifting that rock, all the work you're doing to push that charge against the electric field, it doesn't just vanish. It gets stored in the system, and that increases its total electric potential energy. Think of it this way. The electric field is trying to push that charge away, but you are forcing it inward. So from the field's point of view, it's doing negative work. And this points to a really important rule in physics. When the field does negative work, the potential energy of the system goes up. All right, so now let's see how this whole concept works when we actually build a system of charges, putting them together one by one. This is how we can figure out the total potential energy. We're going to follow a simple 4-step process. We'll bring each charge in from super far away and stick it on the corner of a square. Okay, step 1. We bring in our first positive charge. Now, since there's nothing else around, no other charges, no electric field to push against, it takes zero work. It's like rolling a boulder onto a perfectly flat plane. No effort at all. Now for the second charge, as we bring this one in, we actually have to do some work. We have to push against that repulsive force from the first charge we put down. And the amount of work we have to do is exactly equal to the potential energy that's now stored between these two charges. Okay, bringing in charge number 3. This is where it gets a little more interesting. Now, we have to push against the fields from both of the charges that are already there. So the work we have to do is the sum of the work it takes to fight charge 1's repulsion plus the work to fight charge 2's. And finally, we bring in that 4th charge, doing work against the other 3. The grand total of all the work we did in every single step, adding up all those little interactions, is now stored as the total electric potential energy of the whole system. That's the energy that would be unleashed if we just let them all fly apart. So, we're getting a handle on the energy of a system of charges. But this leads us to a really closely related and incredibly useful concept: voltage. Think about this. The potential energy depends on the actual charges you're putting into the field. But what if we just want to describe the electric hill itself, without having to talk about the size of the boulder we happen to be pushing up it? How could we map out that energy landscape? Well, that is exactly where electric potential comes in. All we do is take the potential energy, U, at any given point, and we divide it by the charge, Q, that's sitting at that point. This new thing, which we call V for voltage, gives us a property of that location in space. It's the potential energy per coulomb at that specific spot. And this difference is absolutely crucial. Potential energy, U, is the total energy stored, and we measure it in joules. It describes the specific boulder on the hill. But electric potential, V, or voltage, is the energy per charge, measured in volts. It describes the height of the hill itself, whether there's a boulder on it or not. And that, right there, is the key takeaway. Voltage isn't energy. It's the potential for energy. A 9-volt battery doesn't contain 9 joules of energy. What it means is that for every single coulomb of charge that moves from one end to the other, it has the potential to do 9 joules of work. It's a pretty wild idea when you think about it, that energy is just stored in the very fabric of space, in these fields we can't even see. It kind of makes you wonder, if electricity has its own invisible landscape of potential hills and valleys, what other unseen forces and fields are out there, storing energy and shaping our world in ways we haven't even figured out yet?